Hello everyone, my name is Trần Hu Nhật Huy, a third-year undergraduate student of Tokyo Institute of Technology. Today I take great pride in participating in this conference with my research topic, Simulated Gaze Tracking using Computer Vision for Virtual Reality. Now I would like to start my presentation. As virtual reality is becoming more viable for creating immersive learning environments, a promising area of study is monitoring and assessing learners' engagement. The most way to do this is through gaze tracking, a biometric technique that can monitor and follow a person's eye movement in real time. However, recent improvements on gaze tracking focus on improving hardware capability, such as tracking modules or attachable lenses serving as add-ons for VR headsets, resulting in high cost which is undesirable for educational applications. So our idea is to propose a non-hardware algorithmic approach in order to reduce the hardware dependency of current gaze tracking VR headsets, based on video processing techniques and computer vision algorithms. Recent advancements primarily focus on integration of hardware devices. Devices such as Microsoft's Kinect, Adobe's eye tracker use near-infrared light to track eyes movement through a combination of depth sensors and RGB cameras. Usually, these kinds of hardware are not available in cheaper prices compared to other non-eye tracking headsets such as Oculus Quest. Another work, as cited in the citation below, tracks eye movement through a combination of mathematical convolutions and coordinate grids. This approach does not require infrared-capable hardware, but a dedicated camera is still needed. In this research, we would like to propose a possible method of gaze tracking which does not require additional hardware, focusing on the contents and features that are concentrated by the users, which is crucial in educational planning. To test the validity of our gaze tracking method, we will test it on 3 different videos. First one is a toy video, which is a simple panning motion recorded on a clean background with clean objects. The second one is a VR screencast, recorded from a novice VR user with little to no background changes, but significant changes in features, which we cannot conduct panoramic joining. And finally, the third one, a Mozilla's sample web XR video, which features both types of animation mentioned before. This is the most common type of VR experience. For the Type 1 video, the process involves 5 steps. First, split the video into multiple frames. Second, we conduct panorama staging or joining to merge all frames into one view. Third, we conduct salient object detections on each frame and on the panorama view. Fourth, we conduct features matching between salient objects on each frame and the panorama image. And finally, we plot a heat map showing appearance intensity of those salient features on panoramic image. For the Type 2 and Type 3 videos, the process is basically Type 1 excluding everything about panorama and feature matching. Now, we will use Type 1 videos, the toy video, to introduce the method. First, we split the video into frames, as shown in a video with 5 frames per second. Next, we conduct panoramic joining to merge all frames into one. It is only for Type 1 videos. And then, we conduct salient object detections. On each frame, we select a number of most significant regions of interest, based on a heuristically defined function as shown on the screen. The closer a bounding box is to frame center and the bigger it is, the more significant it becomes. Then, we conduct feature matching. From the regions of interest detected in each frame, we try to find their features in the panorama image and log their coordinates. Finally, we plot the heat map of those coordinates onto the panoramic image. Now we have a visualization of positions where the VR user might focus in. Now I will show you the result of Type 2 and Type 3 videos using the alternative workflow which does not involve panoramic joining. As we can see, the accumulation of salient locations on the heat map is shown throughout the record duration. The same behavior is also observed in Type 3 video with alternative method. As we can see from the results, the first workflow derives a good heat map for Type 1 video. However, panoramic joining process is vulnerable to cases with inconsistent background changes. Thus, it cannot be used on Type 2 and 3. On the alternative workflow, we did not test on Type 1 since it's unnecessary. But for Type 2 and Type 3, although it ran smoothly, the needed information of gaze tracking is not easily deducible. This makes alternative workflow inappropriate for VR gaze tracking. As you can see, besides some acceptable results, there are still many limitations. First limitation is the difficulty of generating an overall representation of immersive environment. Real VR recordings include inconsistent rotations in users' viewpoint, object and feature changes, motion blur effect, and others. This makes panorama buildings from VR recordings challenging. The second limitation is the accuracy of significance function. This function is empirically derived after a set of test runs on different experimental records. Although it detected the most important salient regions, as you can see, more work will be needed in developing a better function with better detection capacity and accuracy. The final limitation is the workflow's performance. As most of the process focus on image processing on the pixel scale, the time required for a recording exponentially increases with the record's length and resolution. It is imperative to enhance the performance efficiency of the workflow to adapt longer durations and higher resolutions. And now I'll talk about possible enhancements in the future. For the significance function, a possible approach is to enhance the function through further test runs to find optimal weighting ratio sets. The possibility of using other functions may also be considered. Stronger image processing techniques within and outside OpenCV's libraries will be explored to achieve higher performance overall. The final goal is to match the performance of VR real-time eye tracking modules currently in use. Finally, we plan to derive a polar coordinate for construction of the panoramic view to resolve cases with inconsistent viewpoint changes. We aim to utilize gyroscopic data acquired from VR headset sensors, but this is less prioritized since it will involve hardware dependency, which is undesirable for our scope of purpose. And this is the end of our presentation. Thank you so much for your listening.